Welcome to The Explainer. Have you ever used an AI to write creative fiction or even just a short story and felt like something was just, well, missing? Like it's technically correct, but completely hollow? If so, you are definitely in the right place. Today, we're exploring the absolute cutting edge of computational narratology through a fascinating 2026 paper by Levent Bulut titled, Can AI Understand Stories? We are going to unpack the actual under-the-hood mechanics of why artificial intelligence struggles so profoundly with creative writing.
It's a question we've all probably asked ourselves recently, right? Why does AI write such flat stories? It's kind of a wild paradox when you think about it. If you ask a large language model to summarize Shakespeare's Romeo and Juliet, it's going to give you a perfectly articulated, flawless synthesis of millions of academic essays. But if you ask that exact same model to write an original, emotionally complex scene, it almost always spits out generic, soulless prose. It lacks spark. It completely lacks tension. So what is the machine actually missing here?
Okay, let's dive into this. Here is our roadmap for today. Number 1, the AI storytelling illusion. 2, told mode versus shown mode. 3, summarization bias and subtext. 4, information friction and entropy. And finally, number 5, the empirical proof and the actual risks to the publishing industry.
Part 1. The AI storytelling illusion. Perfect syntax versus narrative depth.
Bulut's narrative and engineering framework makes a pretty bold claim. It argues that what we perceive as AI story comprehension is actually just an algorithmic illusion. It's essentially a sophisticated manifestation of statistical pattern matching rather than any genuine narrative understanding. You see, authentic story comprehension demands way more than just mapping surface vocabulary beautifully. It requires processing unstated subtext, that inferential layer, where meaning is deliberately withheld so the reader has to construct it in their own mind. That is where true literary meaning actually lives, and current LLM architectures completely collapse when trying to evaluate that hidden layer.
Let's move to Part 2, told mode versus shown mode, the core mechanism of storytelling.
We've all heard the classic writing advice, right? Show, don't tell. Well, let's look at this through Bulut's operational regimes. Take told mode, for instance. This is where emotional content is stated explicitly, right on the surface. Something like, he was deeply loyal and filled with intense fear. The reader doesn't have to do any inferential work there. But now compare that to shown mode. Here, surface labels are strictly suppressed. Instead, the emotion is encoded into objective physical cues, things like thermal gradients or a shift in spatial constraints. AI achieves near 100% accuracy detecting those explicit labels in told mode, but it is virtually blind to the suppressed meaning in shown mode. This brings us to what Bulut calls objective projection. It's a methodology where those surface emotional labels are suppressed, and the content is instead encoded into physical parameters for the reader to reconstruct internally. Think about how we read. Human writers use physical simulations to engage our nervous system, which is our universal biological interface. When we read about trembling hands or maybe a sudden drop in room temperature, our own biological systems metaphorically respond. AI algorithms? Well, they lack a nervous system, so they simply cannot run those physical simulations. All right, Part 3, summarization bias and subtext. Why AI explains everything.
Now, what's really interesting about this is why AI explains everything. Why do its characters constantly and explicitly state their emotions? It boils down to something called summarization bias. Bulut formalizes this as a systematic tendency in large language models to collapse inferential shown mode structures right back into abstract told mode summary labels. Because AI models are optimized for token probability distributions, they literally consume all the inferential work ahead of time. They take those beautiful subtle physical cues and flatten them into blunt summary declarations. It basically ruins the subtext by doing all the decoding for you.
To actually measure this, the framework uses the Suppressed Information Index, or SI. This is the count of unstated information units per minute of reading time required for discourse coherence. In plain English, how much work is the reader being asked to do? When an AI processes or summarizes a piece of fiction, its summarization bias drastically depresses this SI score. It just continually pushes it down, eventually dropping it all the way to 0.
And the paper doesn't mince words about the consequence of this. When SI drops to 0, true narrative comprehension is impossible. Without suppressed information for the human reader to actively decode, the prose loses all of its literary intensity. It stops being a living, breathing story and just becomes a sterile list of facts.
Section 4. Information friction and entropy. The physics of literature.
Here is where things get super cool, because we start treating storytelling as a closed thermodynamic system. This is Bulut's core equation for narrative entropy. S sub n equals the integral of I sub f times C sub b dt. It basically shows how the momentum, pacing, and climactic resolution of a narrative operate mathematically over time. Don't worry, we're going to break down exactly what these variables stand for and why AI completely fails to balance them.
Okay, so IF sub stands for information friction. That's the actual effort the reader exerts to decode the text. C sub b stands for causal branching, which represents the potential resolution pathways of the story. Basically, where could this plot go? Now, as human readers, we naturally sense this dynamic balance between friction and branching. We literally feel the tension building. But large language models, they fall into token probability traps. They physically cannot balance these forces because they have no way to sense the friction they are creating.
And because they can't balance these forces, AI tends to fall into two very distinct failure states. On one hand, you have narrative inertia. This is where the AI eliminates all the friction, resulting in that hyper-predictable, super-generic prose we all instantly recognize as AI-generated. On the other extreme, you get chaotic noise. This is where the AI introduces random, wild chaos that has absolutely no causal grounding in the actual story. Because the machine doesn't have a biological interface to sense what Bulut calls narrative heat, it can't construct a true climax or thermal discharge. It just sort of wanders around statistically. Which brings us to our final section, Part 5, the proof and the risk, empirical evidence and the danger of LLM as a judge.
Bulut's doctrine is not just theoretical. It is rigorously backed by empirical benchmarks. The researchers tested 5 major model families on 100 held-out scenes, specifically trying to identify inferential rules like materialized metaphors. That's where an abstract inner state is encoded into concrete physical details. The target was 9. A blind human rater correctly identified exactly 9 positive instances. The machines, they were hilariously lost. Grok found 0. ChatGPT 5.5 guessed 40, and Claude Fable 5 aggressively hallucinated 78. They aren't comprehending the text at all. They are just making uncalibrated, chaotic guesses.
So, the crucial point is really driven home by this statistical reality, a Cohen's-Kappa score of approximately 0.00 to 0.02. That practically non-existent score proves that machine versus human agreement on inferential subtext remains strictly at chance level. If you are using an AI to detect deep subtext, you honestly might as well just be flipping a coin.
And this data reveals a massive, massive danger for the publishing industry. Think about it. If automated pipelines start using LLMs to evaluate incoming manuscripts, they will actively penalize rich, multi-layered, shown mode prose. The AI will incorrectly code those brilliant physical cues as ambiguity or missing data. Conversely, it's going to reward flat, declarative, told mode prose, simply because it's easier for the machine's statistical model to parse. Deploying AI judges essentially imposes a destructive selection pressure on literature, systematically filtering out complex, beautiful storytelling in favor of flat, machine readability.
Which leaves us with a pretty critical, almost chilling question to ponder. If automated AI pipelines systematically filter out our complex, inferential subtext, what actually happens to the future of human literature? Story comprehension is the synthesis of physical projections interacting with our human biology. It is absolutely not merely the processing of words. Thank you so much for joining me on this explainer today. I highly encourage you to reflect on the true cost of outsourcing our narrative evaluation to statistical machines, and what that might mean for the stories of tomorrow. Keep learning, and I'll catch you next time.